Okay, integrals. So second video on doing integrals. Last one was on indefinite integrals, where we're just making another equation. To definite integrals here, now we have some bounds in this, so we can simplify things a little bit, makes our lives a little bit easier. So definite integrals here. So let's return to position, velocity, and acceleration. So it's supposed to have a position graph that follows this function. So my position at any point of time t, that I can find my position for this. So at position at time of 10 seconds, that's going to be 300 plus 4, so 304 meters. So again, let me walk you through the process and a reminder of a few things. So one, I could take the derivative of this to get to velocity, right? So I could take my derivative with respect to time of position, and this is going to get me to velocity. Again, just remember how I do this. So I'm going to take the exponent and multiply everything by that exponent, and then decrease the exponent by 1. So I'm going to have 6t here. I have an exponent essentially of 0, so when I multiply everything by that 0, I get 0. So I'm going to be left with 6t. And this is an equation for velocity at some time point t. So a definite integral means that I'm going to be interested in just a section. I'm going to be interested in a particular time point in this case. So I can say, well, I'm going to be interested in what's happening between time equals 0 to time equals some time point. I'm interested in some time point from time equals 0 to some time equals t. So how I'm going to do this, so I'm going to do the same stuff. I'm going to take an integral of this 6t with respect to time. But now I'm going to bound it. So I'm going to say, well, I'm going to start at t equals 0. I'm going to go to t equals the final time point t. And the math is going to be the same. We're just going to add one extra thing in there that's going to help us get rid of a constant. So when I do this, right, so I'm going to take the integral of 6t. Remember how I do this? So I'm going to add 1 to the exponent. So I'm going to have t squared. I'm going to divide by that new exponent, so I get 3t, so close. But I don't know what else is there, so I have some constant there. Because this is a definite integral, I'm going to evaluate this. So I'm going to evaluate this from t equals 0 to t equals t. And by evaluate, we mean final minus initial. So evaluates final minus initial. So I'm going to plug in my final, get some equation for that. I'm going to plug in my initial, get some equation for that, and subtract the two. So when I do this, right, importantly, it gets rid of my constant, right? So this is telling me essentially the change in displacement. So my final, I'm going to have 3. I plug in t for t, so I get t squared plus c, right? That's my final when I plug in t. And I'm going to subtract from that my initial, which is now 3 times 0 squared plus c. This goes away, and notice that I have a positive c and now a negative c, and my constant goes away. So definite integrals allow us to ignore the constant, and all the math works out. So in this case, I end up with 3t squared. Notice this is slightly different, right? So this is telling me what's my change in displacement across this time interval that I'm interested in. It doesn't tell me my starting position, so there's more information in this original equation, but I don't care about it here, so I just want to know my displacement, my change in displacement. Okay, let me walk you through one example of this. That's as complex as it gets right now, so there'll be a few other things that we'll need to take integrals of, but for right now, getting a handle on the power rule and the constant, and when you get to ignore it, is probably the most important thing. So let me go through an example. So suppose acceleration at time we were given has some function that we're interested in, which goes like 18t plus 1. Why not? So if I want to find the velocity between time point 0 and time point t, which is a reasonable thing to do. So between t equals 0 to t equals t. So I'm going to take the and then we're going to go on further. We're going to find what's the displacement between those time points as well. Right? So first I'm going to take the integral of this. So my integral of this thing with respect to time, I'm going to go from 0 to t. So notice I did a little shorthand here because I'm lazy. I don't feel like writing it all out, but when we have more than one variable in an equation, it's going to be important. But for right now, this is fine. So I'm going to take this. So what happens when I take the integral of this? Well, let's see. So I'm going to raise the exponent to 1. So I'll have t squared. I'm going to divide by my new exponent, so I'll get 9t squared. Now this one, I'm going to assume this is t to the 0. I'm going to raise my exponent to 1, so I'm going to have t to the 1. I'm going to divide by that new exponent, which is 1, so I'll just be left with t. I'm going to evaluate this from 0 to t. Recall my constant is going to drop out, so I'm going to be left with just this equation. So this tells me 9t squared plus t, and that's equal to, now, my velocity at any time point. Again, remember, this is what this is telling me. So this is not telling me my absolute velocity. That's telling me my velocity change within this time frame, but good enough for what we need. So we're going to get to position. So how do I get to position? Well, I can take the area under the curve of a velocity graph to get to change of position. So we can take the integral of this. So the integral of this 9t squared plus t is going to tell me, it's going to give me a function for position. So I can evaluate this over the same time frame, right? So I'm interested in going from 0 to t. It's a definite integral with respect to time. So now I'm going to do the same sort of thing. So I'm going to say I have my exponent here. I'm going to raise my exponent, add 1 to my exponent, and divide by my new exponent. So I'll have 3 here. For this, I'm going to add 1 to my exponent, so I'm going to have t squared, and I'm going to divide by my new exponent, so I have 1/2. This is my new function. Since it's a definite integral, I'm going to drop the constant because I know it's going to go away, and I'm going to evaluate it from 0 to t. 0 is not going to be anything, so I know my position, time point t, is this function 3t cubed plus 1/2 t squared. Again, be careful what it's telling you, because right now this is a definite integral, which means this is telling me my change of displacement. So this assumes my starting position is 0, assumes my starting velocity is 0, and that's that's going to get me there. But anyway, hopefully you get the idea that you can use the definite integral to look at a particular time, in this case time-bounded area, and it makes the math a little bit simpler. But the way we make integrals is still the same, and the interpretation of the integrals, the area under the curve, that is still the same as well. Hope that helps. Talk to you soon. Bye.